Okay. Um, so yeah, when we talk about the sample space, we're considering all possibilities of a certain experiment, of a certain action that we're trying to enumerate the outcomes of. Um, and then we talked about the three axioms of probability, which means that the probability of an event occurs, the numerical output is between 0 and 1, including 0 and 1, but nothing above 1, nothing below 0. The probability that something occurs in your sample space is 1. It's almost obvious to say that something in your sample space is going to occur if you were to perform the probability experiment. So that's what that means. And this is more like the third axiom here is more of a set theory axiom. Um, and yeah, the real axiom is right here. So if you have a union, we talked about union, right? So it's just saying that if we collect a whole bunch of events called E sub I, and there's E sub 1, E sub 2, all the way to E sub n, and each of these groups are mutually exclusive. And we're going to talk about more about this to make it clear what it means. Mutually exclusive just means that each of these events, there's nothing in between them that is in common with one another. They're also, you can also use the word disjoint. They're quote unquote disjoint. So you can see that these circles here don't overlap. So henceforth, they're mutually exclusive. And when you take the union, and this is just a big union, right? Instead of writing all this out, you use a big union symbol. And then these are like the indices. They tell you that I goes from 1 all the way to n. So this kind of works like the summation notation, where the bottom indicates where the starting index, and then this is counters up by 1, and the limit here is, and the top boundary is n. So when this occurs and you have a union of mutually exclusive events, then the probability of that union of mutually exclusive events is equal to the sum of each event occurring, and you add those probabilities all up. So that's the idea behind, and this is important because you'll see this as we get more sophisticated with our probability concepts. And then we defined what probability was, which was the probability of an event is the probability found by taking the fraction of the number of ways that a certain event occurs divided by the total number of outcomes, which is the same thing as saying finding how many things are there in the sample space. So the denominator indicates the number of outcomes or things in the sample space, and the numerator indicates the number of ways of having the event E occurring, whatever that E is. And then we saw some examples, and then we finished with a little bit of help with the punching hole problem, the Hungarian problem. Okay, so let's make sure we break some stuff down. And I want to go back to what are mutually exclusive events. So mutually exclusive events. So again, what are mutually exclusive events? They are events that, there's several ways you can explain this, right? There are events that cannot occur simultaneously. So I guess I can give you several definitions. So that's one way to interpret it, right? They cannot occur simultaneously. And I'll give you some examples of what that means. The second way to think about it is that these events are represented by disjoint sets. Now, what does that mean, disjoint? What are two sets that are disjoint? Well, it means that there is no intersection between them, right? No overlap. That's right. So one thing about learning mathematics, learning probability, is knowing how to say things in English and how to interpret that or express that in mathematical notation. So when I say disjoint, that's very good. That means that there is no overlap. No overlap between sets. Now, how do you say that? Or how do you express that mathematically speaking? So this is where we say no overlap between sets can be represented by. So a third way, this is more of the mathematical notation, is that if E and F are mutually exclusive sets or mutually exclusive events, then E intersect F means that this, so each of these definitions mean the same thing, but they're kind of seen from a different perspective. So the first one, we just consider them as sets, and we're considering them as a certain action being performed. One action cannot perform at the same time as the other one, so they're mutually exclusive. The second one, we're considering it as things that don't have a common outcome, or they're called disjoint, or there's no overlap. And mathematically, notation wise, we say that E intersect F. So this upside down U means intersect. The intersection between these two sets is what's called the null set. This is the set that contains nothing, if that even makes sense. It's in the set that has nothing in it. So sometimes we write it like this with the little zero and the slash going through it, or we write two curly braces and indicate that there's nothing in it. So these two things mean, or this is called the null set, also known as the empty set. It's synonymous in this class, in this field. So it's the set that has nothing in it. So then pictorially, what does that mean? Pictorially, how can we draw this? So let's suppose we have again, it's very simple here. We have a sample space, and then I'm going to draw an event indicated by a circle, call it F. And then I'm going to have, let me draw this. Let me use yellow for this here. And then this will be F. So all of these things here are the same, representing the same idea of what are called mutually exclusive events. And using axiom number 3 of probability, so using axiom number 3, so using the probability axiom. Then if we have mutually exclusive events, the probability of E or F occurring is equal to the probability of E, parentheses, plus the probability of F. And we can use this, we use or, right, interchangeably with the union symbol. So you may see this much more, E union F. So again, this only occurs if we have mutually exclusive events, E and F. So let me write this. If we have mutually exclusive events E and F, then the probability of E or F occurring is a probability of E plus a probability of F. So this only occurs with mutually exclusive events. So once we have that clear, that definition clear, then we know when to add, right? You know, I think some of you have asked that question before. How do you know when to add? And how do you know when you multiply probabilities? So one prerequisite to add is the fact that these events are disjoint. These events are mutually exclusive. These events don't have an overlap. These events don't occur simultaneously. So if you have that, then you add. So then that's when the understanding or the interpretation of our problems become very important to understand whether the events that we're considering are indeed disjoint, meaning mutually exclusive, or if they're not. So again, with the standard 52 card deck, right, we love using these examples. So a card is chosen at random from a standard deck of 52 cards. So for those of you who maybe at this point still aren't so clear with what a standard deck of 52 cards is, I'm pretty sure you can buy one 99-cent store somewhere, something cheap. It's not that much. So you can just have an idea of what it is. If not, you can Google the image, but I'm pretty sure most of you have an idea, right? So we have 52 cards. We have 4 suits, heart, diamond, spade, and clubs. And what is the question is, what is the probability? So that's my dog. I have a dog. Probability that the card is a queen or a diamond. No, sorry, is a queen or a two, or a 2 of hearts. Let's do that. So what do we see here? We see 2 events. I don't know if you start to see now, try to associate sets, events using when you see these words, right, in the question. What is the probability that the card that we choose at random? So choosing a card at random from a standard 52 card deck, that's the experiment, right? So this whole, we have to start to break down these sentences as what's the experiment, what are the events that we're considering, because when we're able to do that, it helps out with the solving of the problem. So this is the probability experiment. This is what we are like considering, right? This, I should say, experiment. They are mutually exclusive, right? So what do you mean that what are the things that are mutually exclusive? So then this is the queen, right? Getting a queen is an event. And then getting a 2 of hearts is another event. So yeah, you can't have both a queen and a 2 of hearts when you select one card. So that's impossible, right? So because that's impossible, we're considering these 2 events as mutually exclusive. So just to like make sure we clarify things, have that clear. So let E be the event that a queen is selected. I'm considering that as an event. Now, we can be more specific, of course, right? What do you mean by getting a queen? We can get a queen of hearts. We can have a queen of. So we can also enumerate what that means. We can have a queen of hearts. We can have a queen of diamonds. We can have a queen of spade, and we can have a queen of clubs. So these are all the possibilities, right? Right, Oliver, that's right. Or is addition and is multiplication, but we have to be still careful because we're going to see what happens when they're not mutually exclusive, which is the next thing. And then we let F be the event that a two of hearts is selected. And there's only one possibility, right? This is only one outcome. We have a two of hearts. There's only one of those. So set F only contains one outcome, whereas set E contains four outcomes. So then we see, what do we see? We see that the intersection is the null set because there is nothing in common between E and F. Henceforth, they're disjoint. So all that comes with it, right? So we can say E and F are mutually exclusive, aka disjoint, right? They're disjoint sets. Okay. So then, what's the probability that we get a queen or a queen or a two of hearts? Well, we can now write it as the probability that E union F occurs, just the probability that E occurs plus the probability that F occurs. But now finding the probability that E occurs, we have only four possibilities, right? Out of the total 52. So one thing, of course, we always have to specify is that S. What is S? S is the selection of one card, right? Is just the cards, 52 cards. Any of the 52 cards. That's my sample space. So select any of the 52 cards, and that's included in the all possibilities of selecting one card. So that's why it's 4 plus 52, and then we add 1 over 52. So the probability is 5 over 52, and whatever that is, right, numerically speaking, as a decimal. That would be the probability of having a queen or a two of hearts when I select one card at random from a 52 card deck. Of course, this is a simple case of what we call mutually exclusive, right? So is that clear? I'm pretty sure, having done most of the homework problems, you have this clear, but now I just want to make sure that the idea of mutually exclusive events is really clear, utilizing all these four different ways of explaining what that is and connecting mutually exclusive events with probability, and particularly the third axiom in our probability set of axioms. Okay, and now following this, I'm going to use the same example. So we have a 52 card deck, right? We have a standard 52 card deck. What is the probability of selecting a queen or a diamond? Whoops. So you may be thinking, oh, it's the same problem, right? We have a queen or we get a diamond. And we're trying to figure out what's the probability of selecting a queen or a diamond, right? And then you see, oh, it's or, and then you have the urge to add, which is fine for adding the probabilities. But before we add, we have to consider what are these sets, right? What are we considering? So we already let E, right? We already did this. Let E be the selecting of a queen. And I'm just going to write it as the queen of hearts, the queen of diamonds, um, the queen of clubs, and the queen of spade. Now, what's the issue, or what do you see? Right, Saring? Queens can be diamonds. So then if we say let F be the set of outcomes where the card is a diamond, we have 13 ways for a card to be a diamond, right? We can have an ace of diamond. We can have the 2 of diamonds. We can have the 3 of diamonds, dot, 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 all the way to the 10 of diamonds. We can have the jack of diamonds. We can have the queen of diamonds, or we can have the king of diamonds. Now, or I should say are, E and F mutually exclusive? And the answer is no. No, because why? The intersection of E and F is not the null set, or I should say the empty set. It's not that. What is it? The intersection of E and F is what? What's in both of them? It's in both, right? So the queen of diamond is in both sets. So then so they're not mutually exclusive. So then how do we find the probability that it's a queen or a diamond? Remember, the formula that we had with the addition is only possible if the two sets are mutually exclusive. But now we have two sets that are not mutually exclusive, and I want to find the probability of that union. And then we have this idea that Alexandra brings up, very good. We quote unquote subtract the overlap. And why is that? So this is where drawing helps. And people like drawing this, right? This little Venn diagram. So let's call this F, and let's call this F. Pardon. Let's call this E here and call this F. Okay. Let me just write this as this now. The probability that E union F, right? That's what I'm trying to figure out. Now, when we talk about this region right here, we're talking about the intersection between E and F. Now, normally, what do we normally do when we consider the probability of two disjoint mutually exclusive events? We find the probability of one, and then we add it with the probability of the other. In doing so, for sets that are not mutually exclusive, that have an overlap, if I count the probability of E, right, I'm considering this portion here. And then when I count the probability, or I tabulate the probability of F, I'm also counting this region again. So in a way, when I do this, right, when I do the probability of E, and I do have to add it to the probability of F, I have to subtract the probability of the intersection. Why is that? Because then if I just do these two things here, I am overcounting, quote unquote, whatever's inside twice. I'm overcounting that event. That's what would have happened if I just added these two probabilities. So in order to count this overlap region just one time, I have to subtract the probability of this occurring because I'm already counting it twice in this sum. So that's why it's going to be, what's going to be the probability? What's the probability of E happening? Well, the probability of E happening is 4 out of 52 ways, right? Queen. What's the probability of getting a diamond? Well, there's 13 diamonds in a set of 52 cards. So we add by 13 over 52. But then I have to subtract that overcounted event, right? The overcounted event is this one. I count this one twice in adding these two probabilities. So I have to subtract one of them out of the 52. Right? So then now we're just adding fractions together. When we add 4 plus 13, we get 17 minus 1, we get 16 out of 52. And then if you want to reduce this, you could divide by 4 and I get 4 out of 13. So the probability is of getting a queen or a diamond is 4 out of 13. So everyone understand why I had to subtract that overlap region to correctly find a probability. So in general, the probability of A union B, right? A or B is the probability of A plus the probability of B minus the probability of A intersect B. And this idea is called the principle of inclusion-exclusion, or the inclusion-exclusion principle. Okay. Is that clear? So we talked about probability of a union of mutually exclusive events. Now we've talked about probability of a union of sets that are not necessarily mutually exclusive. Okay, so we have to consider the overlap region. Now there's one probability experiment that I want to consider, and it's the probability. So let me talk about a new probability experiment. Which is rolling 2 fair 6-sided dice. And I want to find the sample space, right? The sample space of the above event. How does one enumerate them? Like how do you express the sample space of this experiment, probability experiment? I roll 2 dice. So how would you think we would write them out? Six times 6 squared. Hijab. Yes. So okay, you've counted the number of ways. So we have 36 outcomes. Okay, very good. 36 outcomes. How did you get to that? One, two, three, four, five, six, twice. What do you mean by twice? Times 2? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's what you mean? So you're close. So how do we write this out, right? Right, you can also think of it that way. That's right, Hijab. You do this and this, right? And then you say, hey, there's 6 choices for this guy. There's 6 choices for this guy. So 6 times 6 is 36, right? But I just want to make sure we do something like this. We can see it in this way as a grid of pairs of numbers. So we can consider this is the first row and the second row as an outcome. So we have one being, we can have roll a one and then roll another one. That's the first, I guess, one event, right? Then we can consider that we roll a one the first time and then we roll a two a second time, the second roll, and then so on and so forth, right? And then we can say, well, what if the first roll is a two and the second one is a one? What if the first roll is a two and then a two, and then a two, then a three, then a two, then a four, right? Do you see this? And then we can keep on going. I hope you see that we can go all the way down to having the first roll being a one, a six, and then the second roll being a one. And this would be a six, comma two, right? This goes all the way to what? A six, comma six. So without having to write all of it out, you would have 36 outcomes, right? You would have, you can say this is a row of 6 outcomes and there's 6 rows. So 6 times 6 is 36. Now, why did I do this? Why did I do this? Because what if I say, what's the probability that when you roll 2 dice, the sum of rolling 2 dice equals 8. Now, how would you compute this? What would you have to do? Well, what is the sample space? The sample space is this whole entire thing, right? This is the entire sample space. So there's how many possibilities of this event occurring, of this experiment? There's 36 ways. But you wouldn't have been able to do that unless you have an understanding of what it means to roll 2 fair-sided die and how to enumerate the outcomes. Once you are able to enumerate the outcomes clearly, then you can have a broad idea of what's going on, right? You have a bird's eye view. So giving the sample space and knowing how to define it and how to find the outcomes specifically helps a lot when we have to find the probability of a particular event occurring. So then how many events or how many outcomes are there in the event of rolling a 2-sided die, a 2 dice that equals or that sums up to 8? How many are they? Anybody? Anybody have an idea? 3 out of 36? I don't know. Oh, okay. So see, sometimes, saying the let things be with the dots don't really help. So let me enumerate them completely. So hopefully you'll see how we do this. Yeah, this is something that you can do once and you don't have to do this all over again, but now you have an idea, right? So this is 3, 1, this is 4, 1, this is 5, 1. This is 3, 2, 4, 2, 5, 2. 3, 3, 4, 3, 5, 3, 6, 3. This is 3, 4, 4, 4, 5, 4, 6, 4. This is 3, 5, 4, 5, 5, 5, 6, 5. And then we have a last row, which is last column, which is 3, 6, 4, 6, and 5, 6. So we have enumerated all of them, right? I think we got more now. 5, either 5, 6. I think the combo, okay. So there's a lot of them, right? So then now, do you see how clearly now it becomes? Because then you say, hey, what two numbers add up to 8? Well, 6 plus 2 does, right? So does 5 and 3. So does 4 and 4. So does 3 and 5. And so does 2 and 6. So now it's very clear, isn't it? Or should be, that this whole diagonal here is the event. This is the event that you roll 2 dice and it equals up to, it sums up to 8. And so now it becomes easy to count, isn't it? 1, 2, 3, 4, 5. So the probability is 5 out of 36. So do you see how now it becomes kind of, people use the word a lot in mathematics, trivial. It becomes trivial, doesn't it? It becomes something that, so order does matter here. Okay, so it matters, yes. It matters because I made it matter. The way I started out, the way I started enumerating the outcomes, I made it matter. I said there's a first roll and there's a second roll. So making this event or making this probability experiment sequential with the first die and the second die, I was able to enumerate all of the outcomes in this manner. So of course, 6 plus 2, 2 plus 6, right? You can just interchange and swap them and they add up to 8, no matter what. But we're considering them as different events, different outcomes, giving you the same result, right? But they're different because it's the first roll is a 6, then it's the 2, or then it's first the 2, then the 6. We made it that way from the beginning. So yes, the order does matter, but I made it matter because I wanted to write it this way. So maybe what that should give you that idea, this idea is that when things become a little more complex and sophisticated, you have the power sometimes in certain situations, such as this, to view things from a sequential perspective or from a non-sequential perspective. And you'll see that you get the same result. So there are certain cases, not for everything, but there are certain situations where looking at it from a sequential point of view is actually more insightful than if you were to not look at it from a sequential point of view. And this is an example of where a sequential point of view of first roll, second roll, it kind of makes sense and everything just like works out very nicely. If you didn't deal with sequence, right, of having a first roll and a second roll, or first roll of a die and then the second die being rolled, if you didn't have that sequence, then differentiating the different outcomes, it becomes a little bit more difficult. So it's natural for this particular example to do that. So this is the sample space. Okay, so I'm gonna call this part A. And then how about part B? Part B. What's the probability that the sum of 2 dice So we always like introducing this prime stuff, right? So what if the sum is prime? What's the probability of that happening? So obviously the denominator, that's the easy one, right? It's 36. But then what would be the number of ways of rolling a sum being prime? So first of all, what's prime? Prime numbers, right? 2, 3, 5, 7, 11. These are numbers whose factor is only 1 in itself. So when we look back at the sample space, what pairs of numbers add up to 2, for example? So let me copy this here so we don't confuse ourselves. And I'm going to erase this here. So we're not considering 8 anymore, right? Because 8 is not prime. So these guys here, no good. So how many are there? So first, for example, this here, this adds up to 2, right? That's prime. And the next diagonal here, what? 2 and 1, 1 and 2, that adds up to that adds up to 3. And then what? 1 and 3, 2 and 2, 3 and 1, that's 4. That doesn't work. 4, 1, 5, 3, 2, 2, 3, 1, 4. All of these here adds up to 5, which is prime, which is what I want. The next diagonal here, 6, doesn't work. And then the next diagonal, 6, 1, 5, 2, 4, 3, 2, 5, 6, 1. All of these outcomes, they add up to 7. That's prime. The next diagonal here doesn't work, right? Because we did that already. That's the 8 one. And then 9, that's not prime. And then 10, that's not prime. And then 11, right? That's 2 of them. And the last one is 12. So these are all the possibilities of rolling 2 dice that whose sum is prime. So then how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 ways. So the probability is 15 out of 36. And then if you reduce this, divide by 3, and you get 5/12. So probability is 5/12. Make sense, guys? So differentiating the outcomes or enumerating out the outcomes in the sample space is nice, especially when we have situations where we have 2 events occurring. And then we're able to kind of like carve out and group our events together, the desired event that we want. So the desired event is that they add up to a prime number. So now it's easy to group them together into, you can consider them as disjoint sets, right? These are all disjoint. They're disjoint. And then we want to find the union of them. And that's why we added the number of outcomes up. So all of this is happening at the same time. That's how we get these numbers 15 out of 36. Is that clear? Any questions about this? So Sering is saying, if we didn't draw this grid, it would be hard, right? To count them all. So this idea, okay, this is a classic example, right? This experiment is a classic example because it kind of shows you. So I know at one point, you're just learning how to count things, right? So you're learning how to use the fundamental principle of counting. So you're learning how to apply those things, and then eventually start to see that, oh, counting is multiplication and all that. And so there's sometimes there are probability experiments where the number of cases or the outcomes is way too big. So we can't enumerate every single possibility. So just finding that number is enough. But now we start dealing with probability, and we do carry over all those counting techniques. But now we have to be a little bit more careful with how we interpret our sample space or our events. We have to be very careful and clear about it. And this is a classic example where just trying to count them like in our heads becomes a lot more confusing compared with actually writing out all of the events out and seeing it in a visual manner, such as this grid. And then hopefully this starts to make you see that drawing things clearly and fully out, especially in this kind of problem, helps a lot, because then finding the probability is just literally you're counting 1, 2 like this. You're literally doing this. And then finding the probability, oh, it's like, oh, 15. Of course, there's only 15 outcomes out of the 36. So it becomes almost trivial. But if I didn't have this grid, like you said, if I didn't have this grid, then either you have, it's kind of like you must have seen this grid before, or you interpret it as a grid in yourself, in your own head, or you have another way of counting it. You can have another way of counting something. But this is the most like natural way to go about it. Like it's kind of difficult to explain something that's natural, right? It's something it just feels, in this case, to write it out in this grid like manner, it feels right. Is there another way of counting all of these outcomes? Sure. But what would be the better way? This would be probably the best way. Not everything is counted in this grid. No. Sometimes using circles and sets makes things much easier. But in this case, the very structure, the nature of the problem itself, this grid-like structure makes sense. And then clearly it makes sense. It's just clear, right? You just look at it, you circle things, and it's a very nice structure behind this problem. It's very nice. You can see it. And now that you've seen it, you can't unsee it. Like now you're only going to see this problem using the grid. That's the kind of thing that happens, right? When something's natural, when you see it, it's like, oh, you can't unlearn it. Like it just feels right now. It feels like this is the appropriate way to go about it. Okay, so this is a very good example. Okay, great. And so let's continue on with these sets and probability. We talked about the complement, right? So finding complementary probability, we talked about that. So we like using so if we call this E, right? I'm gonna use E. Your book likes using E a lot. So if I want to find the complement of a set E, then it's the same thing as saying 1 minus the probability of E. And sometimes we like using the notation E with the bar over it. So these two things are the same, okay? So if you see E or a set with a bar over it on top, it's the same thing as saying the complement. Now, why is this true? Why is this true? Can anybody tell me why this is true? Sample space, right? And what do you mean by that? It adds up to 1. So again, a picture is worth 1,000 words, right? So when we consider the sample space, remember the sample space, one of the axioms is what? The probability. So this is the axiom, right? Axiom, I think it was number 2. The probability of the sample space is 1, right? The probability of anything in this in the outcomes, in the set of all outcomes, right? The probability of one of those things happening is gonna happen. So it's 1. And what we do is we call E a subset. It's a set within a set. So E is something inside of S. It's something. It's a collection of events inside of S. So this is E. So everything outside of it, everything that's not in E is considered to be C, the complement of E, which is E with the little c, right? So then what is S? S is E union E complement, right? If we take E and we take everything that's not in E and we union it, then we get S. And what else do we see? What else do we see? What do we see? We see that E intersect E complement is what? Mutually exclusive, right? There, it's inherent, right? You can't have something that's an E and not an E. That's an impossibility. So then we say this is the null set. So they're mutually exclusive. obviously. And so since they're mutually exclusive, when we find the probability of S, this equals the probability of E union E complement, which is the probability of E plus the probability of the complement. But we already know that this sum is the probability of the sample space, which is 1. And so there, henceforth, the probability of EC complement is 1 minus the probability of E. So in a way, we just showed, right? This is the end of the proof, the little proof. So that's why this is true. So this idea of events and their complement sets and their complement set, it's going to become very important, especially when we continue on with probability. But now we have better understanding of how to not just know what they are, right? Not just know what a complement is, but now we're able to determine, oh, these are mutually exclusive. Oh, that means that their intersection is empty. Oh, that means that you can find the probabilities of those unions of mutually exclusive events as a sum, and then so on and so forth. And things become a little bit more clear, I hope. Okay, so then once we have that, good, I think we can now continue the next thing. So that's the probability world. And there's one thing I want to say, maybe this might be the last thing. One key technique in probability that will become very useful is partitioning. It's called this idea of partitioning the sample space with mutually exclusive sets, or I should say events. You'll become very in tune with what I'm saying with what I'm saying eventually. So again, we have this sample. I'm first going to just draw this out. I have a sample space, and I'm going to have an event, some event. So I'm going to call this E. And the idea is this. The idea is that I'm going to try to find a way to partition. Now, this partitioning means I'm just going to divvy up the sample space in a way that every cut, you can say, and every cut that I make right? Every division that I make, so I'm gonna call this A1, I'm gonna call this A2, A3, A4, A5. When I divide it up, there is A1 through A5. These are all mutually exclusive events because they're all disjoint. There's nothing in between them. They're cut up. But what I'm doing is A1, so I'm gonna call this AI are all AI for, and then I'm gonna say this is for I equal to 1, 2, 3, 4, 5. So basically what I'm saying is each one of these guys, right, are mutually exclusive. And of course, having an example will make this a lot more clearer, a concrete example. But I'm just giving you the visualization of this first, because now we're dealing more with this notion of sets and mutually exclusive sets, and seeing it from a visual perspective. But actually, before we go through that, I want to go back to this example, and I want to ask: is there a way to, instead of writing this out every single time, to explain what the sample space is there a way to write this in a shorter notation, in a more compact form? Does anybody have an idea of what that would look like? Yeah, so the book that we have, the Pearson book, I mean the Ross book, um, they have it has a lot. It's like something with I's and J's. Right. So I guess one thing I want to say about like textbooks and particularly math textbooks, right? And you can think about it. This idea of probability, right? It's not that somebody came up with a new way or another version of probability. Probability is pretty much the same throughout and it's the same, right? In any country, any language. It's just that the style of there's so many books about probability, so many books. The style is different. So his style, Ross, he just packs in a lot of examples um and sometimes it's really good examples. Sometimes it becomes a little too theoretical, like he just goes off the deep end. And some problems with some textbooks is that they're so, I guess, a bit more advanced than they normally could be, than they should be. Um, and their notation sometimes is very the idea of sometimes being too compact sometimes, right? You lose the understanding of it. So this textbook is not the kind of textbook that will do this for you. They won't enumerate everything out for you. You kind of have to do that for yourself. But now that you do have this idea, right? When I write what I'm going to write down, I hope it makes a bit more sense. If I were just to give you this from the jump, you'd be like, wait, what? So concatenation. Concatenation, I don't know too much about the concatenation. I think there's another word for that in mathematics. I think it's like called the Cartesian product or something like that. But what I want to say is that to write this, instead of writing all this out, I can just write it like this. So S is the set of. No, it's okay. Don't worry about, yeah. Any ideas is good. So it's a set of I and J, right? Such that I or J is either a 1, a 2, a 3, a 4, a 5, a 6. And that's it. Yeah, there's a whole bunch. And again, what's so special about I and J? There's not really much special about I and J. You can just use any of the two letters of the alphabet, any other symbols, but of course we use alphabets. Right? It's a convention. That's right. Um, so this here is this. So see, if you look at it just from here, and if you didn't have this, sure, maybe you could have thought this out. I'm pretty sure many of you could have. But now, now, now I think all of you, having seen this, all of you may say, oh yeah, this makes sense. Right? Like now this makes sense because instead of writing this all out, I can just compact it down, right? I can say, hey, I could be 1 through 6, J could be 1 through 6. All of those possibilities represents the full out spectrum of my sample space. Okay, so you have to learn how to make things compact and small while at the same time being able to unfurl it out. So that's a skill, right? I tell this to students, like you should be able to see a bird's eye view. So this is like a bird's eye view of what we're doing. You see everything. But at the same time, you should be able to see the detail or like the microscopic view. And this gives you more of a microscopic feel. because I don't have to give you the whole thing to understand the whole thing. Understand? I'm giving you a little piece of it, but then I'm giving you enough information to say, oh, then just apply this from a general perspective, and then you get the whole thing. So being able to look at the bird's eye view and the microscopic view at the same time is a very useful skill in any mathematics class, particularly in this one. Okay, so that's that. All right, so we have a few more minutes left. Good. Okay, so we have an idea, a better idea now of mutually exclusive events. We're able to see now that not all events are mutually exclusive. And in doing so, we have to be careful with overlapping of events. And now we're able to subtract them out. Now we're able to look at sample spaces from a bird's eye view. And this idea of partitioning, we're going to consider again. We're going to consider again. Okay, so now I want to talk about what are called independent. This idea of independence is going to come up again and again. So independent events. So independent events are not necessarily, well, independent events, right? The word independent, you probably think of independent versus dependent, right? So independent events are obviously events that don't depend upon one another, right? So these are events that do not depend upon one another occurring. So one way to define independent events is mathematically speaking. So sometimes this doesn't cut it. Just saying it using words, it doesn't cut it, because the idea is, what does it mean by not depending? What do you mean by an event not depending upon another event? So independent events are events. So if A and B are independent events, then the probability of A intersect B happening is equal to the probability of A multiplied by the probability of B. That's what it means. So if you have two independent events, to make sure that they are independent, find the intersection and see if their probabilities, the product of their probabilities independent separately, if that product is equal to that intersection. If it is, then they are independent. If it's not, then so otherwise, if you have a probability of A intersect B doesn't equal the probability of A probability of B, then A and B are dependent. Okay, so my first question would be, if the probability of A doesn't equal 0 and the probability of B doesn't equal 0, and A and B are mutually exclusive, are A and B independent? So what do you think? If you have two mutually exclusive events, are they also independent? What do you guys think? So are mutually exclusive events independent or not? And why? And you can choose, you can look at the examples before that we talked about independent, right? So if we look at the example the uh, of the queen and the two of hearts, they are mutually exclusive. So are they independent? No. How come, Fang or Daisy? Why are they not independent? They're not going to equal zero. So yeah, if we follow, okay, well, for now, Alexandra, take it as a definition. So it's a definition. We define events to be independent if they're products of their individual probabilities, uh, if that product equals the probability of their intersection. So yeah, now it becomes kind of, even though this is a simple definition, it kind of makes you think about, wait, what do you mean, right? What do you mean if I do this, that they're independent? Well, let's just look at this from the perspective of mutually exclusive events, since this is what we started with, right? If we have two events that are mutually exclusive, are they independent of one another? And so if we look at it from a purely mathematical perspective, right, the probability of A intersect B, well, what do we know about mutually exclusive events? A intersect B is what? The null set, right? The empty set. So what's the probability of the null set? This is when things are interesting. What's the probability of the set of nothing happening? We're under the assumption that when we perform the probability experiment, something occurs. That's kind of also the assumption, right? We're not saying, hey, there's a probability that nothing occurs. So the probability is zero. The probability of nothing occurring in an experiment where something occurs is zero. That's the assumption, right? Like the samples, like look at the sample space for the one we just did. We don't, nowhere included in the sample space is the event that nothing occurs. Does that make sense? There's nowhere here that we're including the possibility that like nothing occurs. No, we're saying that we're assuming that something will occur. And these are all the possibilities of something occurring. So the very nature of the probability experiment is that something occurs. Here, A intersect B, we're saying that there's nothing occurs. There is no way for A and B to occur at the same time. So nothing occurs. The probability of that happening is like almost not possible. It's not almost, it's zero. It's not happening because something's happening. But then what do we know? The probability, we're assuming that each of those probabilities individually are non-zero. So obviously this does not equal the probability of A multiplied by the probability of B. Hence what? Hence what? A and B are not. So you can say mutually exclusive events are not independent. You would think, hey, wait, but they're mutually exclusive. There is no intersection. So they shouldn't be independent, right? It's kind of like a natural thing to think about. I remember when I first thought about this, I'm like, yeah, they're independent, but no, they're actually not independent. They're dependent. Can you believe that? Two sets that are mutually exclusive are dependent. So then if you think about that, why would they be dependent? Forget about the mathematical definition behind it. Think about it just purely on the the wording of it. They're dependent upon one another because if A occurs, B cannot occur. That's why they're dependent. So the occurrence of one event does influence the occurrence or the non-occurrence of another event. Henceforth, they're dependent in that sense. You understand? So then this definition that somebody decided to create for independent events, it makes sense. And it works for mutually exclusive. But this idea of dependent doesn't only indicate that they're mutually exclusive, but I'm just giving you an example or I'm showing you that mutually exclusive events are dependent. They are not independent. You can also have events that are not mutually exclusive, that there is an overlap, that are dependent. It's almost like B depends on the existence of A. Right, that's right. That's exactly right. That's exactly right. So then this idea of independent is a little bit more nuanced, right? You see, it's a little more like it's not as um, face value as what it seems. Um, and also, it's about the independence of events is related to the outcome or the experiment itself. So I'll finish with one of those examples, but I just want to make sure. Yeah. Okay. So I'll just finish with this. So for example, if I have a standard deck of cards again, a standard deck, what is the probability of selecting a heart and a diamond? And I'm going to give you two instances. One is with replacement, and one is without replacement. So what's the probability of getting a heart and a diamond? Well, with replacement, which means that if I select one card, I replace what I selected and I put it back in. So what's the probability of getting a heart? Obviously, it's what? It's a fourth, right? So probability. So we'll call this A and call this B. The probability of A intersect B is what? Well, what's the probability of, wait, hold on. What's the problem? So these are mutually exclusive events. So what's the probability of A intersect B? 0, right? So this of linear independence. What do you mean by linear independence? linear independence. Yeah, yeah. Linear independence. I'm thinking about like linear algebra because we're talking about linear. Yeah. Linear independence. They're not the same. The independence of two events is not the same as the independence if the set of vectors are independent or not. That's a different definition. Yeah. Sorry. So sorry, and then a diamond. So let's do this. What's the probability of A happening? Is a fourth. What's the probability of B happening? It's also a fourth, right? What's the probability that A and B happens? If I select A, right, and then B, what happens? If I select a heart, I have what? A fourth of that happening, right? And if I select a a diamond afterwards, after it's replaced, right? I still have a fourth happening. So this is 1/16th. So in this case, in this scenario, these two events are independent of one another. And that makes sense, doesn't it? If I have replacement occurring and I select one card and it's replaced again, then the event that B happens doesn't really is not affected by A. So they're independent under this regard. However, if there's no replacement, and I consider the probability of A happening, that's a fourth, right? The probability of B happening individually, that's also a fourth, right? If I just consider them individually. But what's the probability of A union B, intersect B happening? Well, what's the probability of me getting a heart? Well, there's what? 13 out of 52 ways, right? Which is a fourth, right? But then what's the probability of me getting a diamond? It's still 13, but it's no longer out of 52. It's out of 51. Because I have one less card due to no replacement, not being replaced. So then what do we see? The probability of A intersect B does not equal the probability of A multiplied by probability of B. Henceforth, A and B are not independent. But here, probability of A intersect B does equal the probability of A and probability of B. It does. So anyways, yeah, sorry guys, I went a little over time. But hopefully that makes sense. I'll stop right here with the recording.